Hey guys, it's me, as you can see. Got a little better setup here. We're gonna do one of the problems from the packet, the one about the lawnmower. This guy right here, right? So go ahead and get your packet out, and let's do it together. This is kind of a long problem, so it might be a little long video, but I'll try to be quick. And then follow along. And I think if you can follow all the steps to this problem, you can. It's going to help you with a lot of the other problems. And I'm going to make more videos on other problems. So let's just start off with this one first. All right. So I wrote down all the variables there. As you can see on the screen, our mass, the force being applied, the velocity of the lawnmower, and the angle of the application of force. So. And a couple of key points here. It does say that the lawnmower is being moved along at a constant speed. Remember that constant speed. And you can see the rest of the question there. So let's go ahead and solve this problem. The first thing it asks us to do is to draw the forces acting on the lawnmower. So it wants a free body diagram. So I'm going to draw a circle that's going to represent the lawnmower for me because I can't draw a lawnmower. So what are all the forces acting on the lawnmower? Well, the first one, of course, is the gravity, right? We always have that's a terrible line. We have a I can't draw straight lines. Close enough. All right. So we have mg, right? That's weight. Remember, that's how we're going to start writing weight now is mg. We also have normal force. That's going to go straight up because we're on a flat surface, so it goes straight up. Normal force. We also have the applied force going down this direction, but it has components. I want you to draw the components always, unless you're told not to for whatever reason. So remember, it's at an angle, right? So it's going to have these components that go horizontally and then vertically down. And it told us the angle here was 60 degrees to the ground. So angle there is 60. And then the last force we have is a friction force of friction. Okay, so there's our free body diagram. Got all our forces in there. And next part it wants us to do is to determine the magnitude of the following forces on the lawnmower. Okay, so that's part A. Part A. I is the weight force. Well, that's pretty easy actually, because the weight force is just mg, right? Weight is always mg. The mass of the lawnmower is mg. The mass of the lawnmower was 5, and g is 10. That's pretty easy. 5 times 10, that's 50 newtons. Cool. All right, easy. How about part II? That's the normal force. Now you might be thinking, oh, cool. Well, it's on flat ground, so the normal force must equal the weight force. Not so fast. Remember, in problems like this, where you have a guy pushing, or somebody, or some agent pushing down on something, right? He's pushing into the ground. He's basically adding a little bit of his own force to the weight. So we have two forces going down. We have this force here going down, and the component of the applied force also going down. Now, this object is moving at a constant speed. That means there is no acceleration, which means there is no net force. So all the forces have to cancel out. The downward forces cancel out with the upward forces. So there's two downward forces. So we're going to add those two downward forces up, and they have to equal the upward force. So they all cancel out, right? So we're not going to actually find the normal force directly. We're going to find it indirectly, right? We're going to find these two downward forces first, which is going to help us find the normal force, right? Because we know if we add these two downward forces up, that must be what the normal force is, but just pointing up instead of going down, right? All right, so let's do that. We're going to find these two downward forces. So we've already found one of them. The weight force going down is 50, right? Plus this guy. Okay, well, what is that guy? Well, it's the vertical component of the applied force. The applied force, so it's the vertical Fy, vertical component of the applied force. The applied force was 30 newtons times, now they want sine or cosine here. Let's see. Well, it's opposite that angle, right? It's opposite. So so you want sine. So sine is opposite. Sine of what? Sine of 60, because it's 60-degree angle. So we do 30 sine 60, and we're going to get that vertical component of force there is, we calculator 30 times 60, 30 sine 60 is 25.98. Let's just call it 26. Make our lives a little easier. 26 newtons. All right. So now we're going to do. So there we go. 50 plus 26. That's 76 newtons. There's your normal force, right? Again, because the two downward forces must cancel out with the upward normal force, right? All right, and then the last part, it wants us to find the friction force. All right, so go up here to do that. Friction force. Now again, we're not going to find the friction force directly. We're going to find it indirectly. We're not going to calculate straight for it, but we know that the friction force here, it's pointing to the left, right? Your left. What? I can't. Yeah, that way. There we go. I can't figure my left and right out. Friction force is going that way, right? But it must cancel out with the force, the component of the applied force going the other direction. So if we can find the applied force, if we can find the applied force here, that component of the applied force, it must equal the friction force because they're pointing in opposite directions and they must cancel out. So we're going to find that component here in order to find the friction force. Okay, so it's the same equation we used down here, except instead of the vertical component, it's the horizontal component. So it's going to be 30, the amount of applied force, times cosine this time of 60 degrees, because it's so it's adjacent, right? This is adjacent to that angle. 30 cosine 60 is 15. So that means that our friction force must be 15 newtons. There you go. All right, so we're done with part A. Let's go to part B. It's pretty quick and easy, I think. Part B just wants us to find the coefficient of friction. Remember, the coefficient of friction can be found using the formula for force of friction, which was mu times n. Well, we found force of friction already. We said it was 15 newtons times mu. We found normal force also. That was 76 newtons. We just divide by 76. Divide by 76 both sides. These cancel, of course. And we get mu is like, it's like 0.19 something. Let's just call it 0.2. Yeah, there you go. Piece of cake, right? Easy. All right. Next part. All right. Part C, the fun part. All right. Now in part C, we're going to find how much work is done by the man, by him pushing on the lawnmower, right? So let's rewrite our variables up here. The mass of the lawnmower is 5. The velocity it's going is 3. The angle was 60 degrees. The force he applied it was 30 newtons. And now time, it's a 4-second interval, it says in the part C, a 4-second interval. All right. Now remember, there are 3 ways to find work. All right, 3 ways to find work. Work equals a change in energy. That's the best way. Okay. Work also equals, though, force times displacement times the cosine of theta. Or work can equal the area under the curve of a force versus displacement graph. Well, we don't have a graph, so we can't use that one. And unfortunately, we don't know the total change in energy here, right? Because really the only energy that's being created or that's changing is heat. We're creating some thermal energy from friction. We're not gaining kinetic energy because it's constant speed, and we're not gaining gravitational potential energy because we're not going up in the air or down. So we're not gaining those kinds of energies, only thermal. And we don't really have a way of calculating the thermal energy here, so we have to use this equation to solve for the work. So we got to do a few other steps. So first we got to find x, the displacement, right? We can do that because we look back and we say, okay, well, he's moving at constant speed. We're going to use an old kinematics equation, x equals vt. We know velocity. It told us in the problem it was 3. And now we know that he's going for 4 seconds. Now remember, this equation only works if you're not accelerating. The problem told us that we're going at constant speed, so we're good. So that means that our displacement, 3 times 4, is 12 meters. Right? So our displacement will be 12. So we'll go back into our equation over here, and we're going to plug in the numbers. So work equals force. Now the force a man was applying was 30 newtons, right? He applied 30 newtons of force times 12 meters times the cosine of the angle of which he was applying that force. So the angle he was applying the force was 60 degrees. So we do 30 cosine 60, and we're going to get 180 joules. Now, is that positive or negative? Well, remember from the drawing that he was pushing the lawnmower kind of down at an angle like that, right? But the horizontal component of his pushing is in the same direction as the lawnmower's movement, which means we have a positive work being done. All right. Part II wants to know the weight force, the work done by the weight force. Well, that's easy. The weight force is straight down. the object's displacement is to the right. That is a 90-degree angle. Remember what you said in class today, Thursday, was that if the force being applied is at a right angle to the direction of the movement of the object, you're not doing any work. 0 joules. Easy, done, 0. All right, I wants to know how much work the normal force is doing. Same thing. Again, normal force is straight up. Object's moving to the right. That's a right angle. 90 degrees. You're not doing any work. Sorry, normal force. You lose. All right, which takes us to part IV, or part 4 there. And that is how much work friction is doing. Now, we can think about it for a second. And then we know, okay, since the object is not accelerating, it's not gaining kinetic energy, and it's not going up or down, not gaining potential energy, so we should be able to intuit that the work done by friction is negative 180 joules, right? Has to be. Now let's see how we know that. Let's go back to our equation. F equals Fx cosine theta. The force of friction was 15 newtons. It went 12 meters. Cosine. Now, what's our angle now? If our lawnmower is going that direction, going that way, but the force of friction is that way, what's that angle? How big of an angle is all the way around? That's 180 degrees, right? So we're going to go 180 degrees here. 180 degrees. Guess what the cosine of 180 degrees is? It's negative 1. So 15 times 12 is 180 times negative 1 is negative 180 joules. So that's our work done by friction, right? Again, it has to be that, right? Because friction is opposing the direction of motion. So in total, if you look at the whole system, if we include the ground and the man and the lawnmower, we didn't do any work, right? Because all those forces are internal. But if we look at just the lawnmower itself, the man does work on the lawnmower, but so does the ground. Right? They're both doing work on the lawnmower. It gets a little weird with the negative work. We just think of the negative sign as a direction. All right, last part was part D. It wants to know what is the net amount of work done on a lawnmower? Well, I just said the net amount of work done on a lawnmower, net amount is 0 joules. Right? It doesn't gain kinetic energy, doesn't speed up, doesn't get raised up in the air and gain potential energy or lose potential energy or slow down or anything like that. So we didn't do any net work on it, right? There's no net work done, right? Now it did move, right? It went from one position to the other position. And it took work to do that, okay? But at the same time as the man is pushing the lawnmower forward, doing work on it to move it, right? At the same time, the ground is doing work on the lawnmower to create heat that opposes the direction of motion, all right? I can see how this is confusing because you think, well, if the guy is doing positive work, then, how can there also be negative work if it's being moved? And I understand your concerns, but you got to think about this. Think about it in pieces. Picture just the man and just a lawnmower, right? Ignore everything else, right? He has to do work on the lawnmower to move it forward, right? Now think about the ground and the lawnmower. If the lawnmower is moving forward along the ground, right? The ground is going to push back in a sense against the lawnmower, and it's going to create some thermal energy in the form of heat. All right, so that's everything for number 1. So hope this video was helpful. I'm gonna make some more later of some more problems. I'll probably do that later this evening, or I'll do it tomorrow, so you have it for the weekend. Have a great evening, and I will see you tomorrow. Bye bye.